Welcome to week 8 of this NPTEL course on coherence and quantum entanglement. This week we will look at some two-photon temporal interference effects like the Hongo-Mandel effect and then the double pass experiment. So let us begin with the first problem, which is based on Hongo-Mandel effect. Here is the setup for the Hongo-Mandel effect. We have a pump beam which is incident on a non-linear crystal, which is typically a BBO crystal. And from this crystal, the down conversion takes place, meaning we get two entangled photons out of it. And then these entangled photons then move and they fall on these mirrors. So if this is the signal, it falls on this mirror. If this is the idler, it falls on this mirror. And after the mirrors, these two photons then meet at a beam splitter over here, this horizontal beam splitter. And after meeting at the beam splitter, they can go to these two detectors, DS and DI. And then we can detect the coincidences by measuring simultaneous detection at these two detectors. So this is the Hongo-Mandel experiment. Now let us first read the question before proceeding. I'm sorry about this. I don't know what happened. Yeah. Okay, so problem 1 has 3 parts. First part is consider the Hongo-Mandel experiment. Assuming theta equals 0 and KD equals 0, find the coincidence count rate of the two detectors. Then part B says find the one photon count rate at detectors DS and DI. Then the third part is a slightly modified variant of the setup is given. Refer to the figure below. Assuming x equals 0, calculate the coincidence count rate RSI as a function of the displacement y. If the central wavelength of each of the signal and idler field is lambda s naught, find the fringe period of the coincidence interference pattern. Okay, so first of all, this theta is the angle of incidence made by the signal or idler photon with the normal to the beam splitter, and x is the displacement of the beam splitter. So this beam splitter can actually move up and down. So x is the displacement of the beam splitter. Here also we have this theta, which is angle of incidence of the signal or idler at the beam splitter, and x is the displacement of the beam splitter. Then we have this y also. Sorry. So this y by 2 is the delay that is being caused over here, this distance by this mirror arrangement. So y by 2 delay here and then y by 2 delay again over here, that makes a total delay or displacement of y. And we are also given KD equals 0, that means it is degenerate down conversion. So the wavelength of both the down converted photons is the same. Okay, so just look at these figures for some time and go through the question once again before I start solving it for all of you. Okay, so let us now start solving. Let us begin with the first part to find the coincidence count rate. Coincidence count rate for this Hongo-Mandel setup, this setup. So coincidence count rate is given as RSI, R1 plus R2, which is from the individual alternatives, and then this is the cross term. Now for a Hongo-Mandel setup, we need to find what each of these terms are. So delta L prime is equal to 4x cos theta, which is approximately equal to 4x for theta, which is approximately equal to 0. Delta L is 0 and delta phi is equal to pi. And how we get that is, let us draw the unfolded paths over here. So we have the first choice for, let me just make some space over here. So first alternative, and I'm drawing the unfolded path, is you have this pump, then the crystal, and first alternative can be when both of the signal and idler get transmitted at the beam splitter. So we want to find the coincidence count rate. Coincidence count means one photon at ds and one photon at di. So both cannot go to one detector, that is not coincidence. So first option can be when both photons get transmitted. So when both are transmitted, they are following the same path. This is both transmitted. Let me bring this little bit down. So alternative 1 is both transmitted. Now in this case, phi S1 is pi from the mirror and nothing from the beam splitter. So this is simply pi. Same for the idler. It is pi from the mirror and nothing from the idler. Nothing from the beam splitter. And these paths are exactly of same length. Okay, sorry, it's not looking same length. I'm trying to make it exactly look like same length. Okay, yeah, now they look like same length. Now the second alternative is both get reflected. In that case, let me copy paste this again. Now in this case, because of the displacement of the beam splitter, the lengths of the paths will be different. And how much different they will be? So the signal photon if that is increasing, then idler photon will all decrease by the same amount. So if this is the balance position, then if this distance is 2x cos theta and this distance is also 2x cos theta, and how this is coming is, let me draw it over here. So if this is the beam splitter, this is the beam splitter in balance position, and let me consider then. So the signal is coming and it is getting reflected, idler is coming and it is getting reflected, and this is the balance position, and this is angle theta. This is at x equals 0. Now if we move this beam splitter, let's say downwards by x, and this is signal, this is idler, then the additional path that the signal will have to travel. So now if I move it, now if my beam splitter is here, so now my beam splitter is moved x downwards, so now my signal has to move an additional distance. Earlier the beam splitter was here, so now my signal has to move some extra distance. And how much is the extra part? The extra part is this part. This part is the extra part. And this will come out to be, so if this distance is x and this is angle theta, so this extra part then is this part is x cos theta. Similarly this part is also x cos theta. Now theta is very close, very small, very close to 0. So this extra thing that you are seeing, that is negligible. So that's how x cos theta from this side, x cos theta from the reflected part, that would make extra path equal to 2x cos theta travelled by the signal, and idler will travel less distance. Idler will travel less distance by the same amount. So earlier idler would have gone this path total. Now it is traveling that much distance less. So for idler, the reduction is also by the same 2x cos theta amount. So that's how we have drawn here signal increasing by 2x cos theta, then idler also decreasing by the same amount, 2x cos theta. And then the phases, there is one reflection from the mirror and one reflection from the beam splitter. So that is pi plus pi by 2 and so from here you can clearly see that delta L prime is this distance, this total is delta L prime, which is 4x cos theta. Delta L is basically the difference of the paths from here, alternative 1 and alternative 2, and since both of them are having this balance at this location, delta L is 0, and delta phi is difference of the phases for alternative 1 and alternative 2. Now here this extra pi by 2 and pi by 2 over here will add up to give this delta phi of pi, because here pi and here pi and pi are the same. Okay, so we can now proceed. Also, we are given that KD is 0. So RSI is then going to be R1 plus R2 plus 2 root R1 R2 . Why? Because here this delta L is 0 and here this KD is 0. So only delta phi is remaining inside this term. And we get this. Why? Because delta phi is pi, cos pi is minus 1 and gamma prime 0 is 1. Sorry, gamma 0 is 1. Now let us consider that R1 is same as R2. That means these two individual paths are means having the same counts. In this situation, we will get RSI equals C1 minus gamma prime 4x. This is the coincidence count rate for the Hongo-Mandel setup. Okay, so take about a few minutes to go through this once again. If you have any doubt, feel free to ask in the chat box or unmute yourself. Take about a minute or two to just digest all that we have just now discussed. Okay, someone is asking me a question about how we got this 2x cos theta. So let me see. So let me just go back here. So someone is saying that it should be different, and I understand where that query is coming from. So I'm running out of colors, but anyway, someone just pointed out that this extra path, this part that is there, this extra part should actually be different. So cos theta will be x divided by that extra path length. So the extra path length should actually be equal to x over cos theta instead of x cos theta, that is x sec theta. But as I mentioned that this theta is very small. And so when theta is very small, this white part over here, which is actually x cos theta, is going to be almost equal to this purple path. Okay, this small part over here is can be neglected. So that's how we have written it as x cos theta, neglecting this yellow part. So this purple part is actually equal to the white part plus the yellow part, and yellow part we are neglecting. Yellow part we want to neglect, and this white part is x cos theta. So from there we get this 2x cos theta. I hope it is clear now. So let us move to the next part now. Find the one photon count rate at detectors ds and di. So when a photon is detected at detector ds, the other photon of the entangled pair can be at either di or ds. Meaning it can either, what can happen is, if one photon is being detected at detector ds, then we can have either a situation of coincidence, that is the other photon goes to di, or we can have a situation wherein the other photon also goes to ds. Meaning if we are looking at this situation of reflection at the beam splitter, so it can go like signal can come and go to ds, idler can also get reflected and go to di. But the other thing is idler can get transmitted and also go into ds. So that's the situation. So in this situation, the one photon count rate at the detector ds will be given as rs is rsi, means coincidence, plus rss, meaning both the photons going into the same detector. Now for rss, the delta phi will be equal to 0, and the other terms, that is delta L prime and delta L, will have same values. same values as RSI. This would mean that delta L prime equals 4x and delta L equals 0. And why this is the case? Delta phi is 0 because both photons going to the same detector, so there is no phase difference. So then we have, oh sorry, I need to change the color of my pen. And again, if we keep R1 equals R2 equals C by 2, then we will get this time with plus sign for gamma prime. So you see that the expression is similar as RSI except for the plus sign. Now, coincidence count rate at the detector DS RS is RSI plus RSS, which is, if you add, then this gamma prime terms will vanish away and you will be left with just a constant, that is 2 times C. And from the symmetry of the problem, the detectors DS and DI are similar or identical, so this will give us Ri equals Rs, which is equal to 2 times C. I hope this is clear. Again, take about a few minutes to analyze. Someone is asking what are the alternatives going to be for RSS. So let me just draw that over here. Why I'm not able to draw a straight line? Yeah, this looks straight, I believe. Okay. So first alternative can be that you have the signal going and then coming at the beam splitter, reflecting, and the idler coming and transmitting. And now this is the balance position, but because of the x displacement of the beam splitter, the signal which is being transmitted, that path will change. This will change, and this change will be of a distance 2x cos theta. The other, and again the phases, so reflection at a mirror plus beam splitter, and for this one only the mirror. The other thing will be of the other one going, meaning the configuration is going to look something like this. Now in this, what we will have is the same balance point, but this time the other path is the one which is getting reflected, so this one will go to x cos theta, and this will be this. So as you can see, again delta L is 0, delta L prime is 4x cos theta, which is approximately 4x for theta equals 0, and delta phi is also 0. All these sum total of phi here, and here it is same, 2 pi plus pi by 2, here also 2 pi plus pi by 2. So these are the alternatives. Now we can move to the next part. The next part is pertaining to this setup, and this setup is used in what is known as quantum lithography. So let me just read out the question once again. Part C says, refer to the figure given below. Assuming x equals 0, calculate the coincidence count rate RSI as a function of the displacement y. If the central wavelength of each of the signal and idler field is lambda s naught, find the fringe period of the coincidence interference pattern. So here we see that the setup is similar to Hongo-Mandel. We just have a few extra mirrors and an extra beam splitter. Now we also know that for x equal to 0, both the photons will go in the same direction in the first beam splitter. Now let me first write it, then I will show it to you why it is the case. So for x equal to 0, which is at the first beam splitter, both the photons go in one direction. And then further, for coincidence count at ds or di, they will go at different directions when meeting at the second beam splitter. Now, the first statement that I made, that for x equal to 0 at the first beam splitter both the photons go in same direction, this comes from this part over here, that when x equals 0, RSI is equal to 0 because gamma prime 0 is equal to 1. So coincidence is 0 for x equal to 0. That means both the photons are going in the same detector, and that can be seen that for x equal to 0, RSS, that means the one photon count rate, is 2c. Sorry, not RS. Yeah. So RSS is 2c. That means both the photons are going in the same detector. So for x equal to 0 at the first beam splitter, both the photons will go in the same direction. Now let us draw the alternatives giving coincidence. Actually, I'm not able to draw parallel lines. Let me copy paste. Seems fine now. This is the first beam splitter, and okay, wait, I should little bit show them slightly separate just for the sake of visualizing. This is just for the sake of visualizing and to show the different paths. So this is the delay, and then we have ds and di and coincidence. Okay, so this is one alternative, and the other alternative, let me copy paste this one and then make edits. Now we will not have this mirror here or this delay. and a mirror here this time. Okay, so this is the second alternative. Now we can draw them in the unfolded path representation. Now the phase is one reflection from the mirror, so pi plus from beam splitter pi by 2, then mirror, then another beam splitter, so pi by 2. And for idler it is a mirror and another mirror. Now here it is mirror plus another mirror, and for idler it is mirror plus beam splitter plus mirror plus beam splitter. And this distance right here is 2 times y by 2, which is equal to y, and this is due to the delay. This delay right here that we have, so this is coming due to that. Okay, now that we have these unfolded paths, we can look at the terms delta L prime, delta phi. So then these are the, so delta L prime is 0 because both these I-signal paths arrive at the same length. Delta L is 0, this part, and delta phi, all the phi's are the same for these two alternatives. Here also it is 2 pi and then 2 pi plus pi, and here also same 2 pi and then 2 pi plus another pi. So now the coincidence count rate, delta L prime is 0 and delta phi is also 0, so only k naught delta L survives, which is k naught y. Now gamma prime 0 is equal to 1, and this is equal to, if we keep R1 equals R2 equals C by 2, and now for the degenerate case, we have RSI equals the following. This is because k naught is wave vector for pump and ks naught, which is wave vector for signal, is k naught by 2 for signal or idler. Now fringe width is nothing but periodicity of cos term, and this is then 2 pi over 2 ks naught, which is the following, because ks naught is 2 pi over lambda s naught. So that's the fringe width. This completes problem 1 on Hongo-Mandel effect. Now we can move to problem 2, which is on the double pass experiment. So let me read the problem. Consider the situation as shown in the figure. This is the double pass setup. Here xs, xi and xp are the displacements of the signal, idler and the pump mirrors from the balanced position at which all the mirrors are equidistant from the PDC crystal. This purple thing over here is the PDC crystal. Calculate the coincidence count rate RSI and the one photon count rates RS and RI as a function of the displacement of the three mirrors. That's part A. Part B. Take xp equals 0. Find a way of moving the remaining two mirrors so that we only see the effect of pump coherence function gamma delta L. Then part C. Take xp equals 0 and find a way of moving the remaining two mirrors so that we only see the effect of the signal idler coherence function gamma prime delta L prime. Then part D. What should be the condition for seeing a Hongo-Mandel type profile, that is a dip in the coincidence count rate RSI? What should be the condition for observing a hump in the coincidence count rate? And then can this dip or hump be explained in terms of photon bunching effect? Then plot RSI as a function of the mirror displacements to show the dip hump profile and plot both the curves on the same plot. Then part E. Usually in a one photon interference experiment, there are more than one ports for the photons to go out. This means that whenever we are observing a minimum in the intensity at one port, the intensity at the other port is at its maximum such that the total intensity is conserved. However, in the above experiment, the two photons don't have any ports other than ds and di. So how do you explain the photon number conservation when we are at a minimum? Where do the photons go? Okay, so first read the question once again. Just look at this setup, take a few minutes to analyze this setup, and then we will discuss the solution. Okay, let us now discuss the solution. So let us begin with part A. And let us draw the alternatives for coincidence. So we have the crystal, this is the first alternative. And now the second alternative. Let me copy paste this. So these are the two alternatives. First one is wherein the pump is coming and gets down converted immediately and goes through these two mirrors MI and MS. The second is when it does not get down converted initially, gets reflected from the mirror MP, and then when coming back it gets down converted. So now we can represent them in terms of the unfolded paths. This is from the reflection at the mirror. Now let us draw for the other. Assume that this was the balance position. Then we have this distance as 2xs, because mirror MS is moved by xs, so going and then coming back, that makes it 2xs. Similarly, this is 2xi and this is 2xp, and here phi p2 equals pi, and these don't have any phases. So now the quantities. Delta L prime is 2xs minus 2xi. This difference over here. This difference over here is delta L prime. Delta L is 2xs plus 2xi by 2 minus 2xp. That is the average position over here minus the average position of this one. This is my delta L. And finally delta phi is simply pi. It is pi plus pi 2 pi minus pi, which is pi. Now the coincidence count rate. And now if we keep R1 equals R2 equals C by 2, so that's how C will come. So if we do this, it's xs plus xi minus 2xp. And because of cos pi plus something, that's minus cos pi of that something, so here will come minus sign. And for degenerate, kd will be 0, so we will be left with k naught xs plus xi minus 2xp, and this is coming because R1 equals R2 equals C by 2 and kd equals 0 for degenerate. Now one photon count rate. Now in this case, if one photon is coming at ds, then the other one will definitely be at di. So for photon reaching detector di, the only option for the partner photon is to go to ds. and vice versa. That is for ds, the other option is di. So the single photon count rates Rs is equal to Ri, which is Rsi. So in this case, you can see the 2 photon count rate is the same as 1 photon count rate. So you will see the 2 photon effect in the 1 photon as well. So even if you do not perform the coincidence, even if you look at only one of the detectors, you will be able to see the coincidence profile. So that's the speciality of this particular setup, that you can see the 2 photon effects in the 1 photon itself. Now part B, we need to take xp equals to 0 and we need to find a way of moving the remaining 2 mirrors so that we only see the effect of gamma delta L. So this is the coincidence count rate when xp equals 0. Now for the condition, the other term, that is gamma prime delta L prime, should be equal to 1. So we come up with this particular expression, that is xs equals xi. This means that we will move the mirrors in same direction by equal distance. Part C is to again take xp equals 0, and this time we want to find a way of moving the remaining 2 mirrors so that we only see the effect of gamma prime delta L prime. So again xp equals 0. This time we want condition for seeing only gamma prime delta L prime. This means that the other term, which is gamma delta L, should be equal to 1. So delta L should be 0. This gives xs equals minus xi. This means that we should move the mirrors in opposite direction. Part D. What should be the condition for seeing a Hongo-Mandel type profile, that is a dip in the coincidence count rate? What should be the condition for observing a hump in the coincidence count rate? And can this dip hump be explained in terms of photon bunching effect? And then plot these hump or dip. So let me write down the coincidence count rate. Now from this, for dip, what we need is delta L 0, so gamma delta L becomes 1, and in this case RSI for the dip is the following. We see this when putting delta L equals 0. So gamma delta L is 0 and cos 0 is 1. And for hump, we need to see the following. We need positive sign over here. And this will happen when delta L is lambda. So when delta L equals 0, this gives me cos k naught delta L equals 1. And this gives lambda by 2, I mean. So this becomes -1, and then we get positive sign over here, and sorry, we also have this term, but this is just a constant. This is constant for fixed value of delta L. And if we look at the plot, then assuming a Gaussian type profile for gamma prime, we will get the dip something like this and the hump to be something like this. And the x-axis is xs minus xi, which is delta L prime for xp equals 0, and here it is rsi, and this is the case for the hump, this is the case for the dip. Also, this dip cannot be explained by photon bunching effect. Why? Because there is no beam splitter here. The photon bunching effect was valid for beam. Photon bunching effect is incorrect, but it was proposed keeping the beam splitter in mind. That is, two photons arrive at a beam splitter and then they get bunched and go to one detector. But here there is no beam splitter, so this double pass experiment actually is a way to prove that the photon bunching explanation is incorrect. So the photon bunching theory is like invalid, because we are able to see this dip even when there is no beam splitter over here. So this dip is just a characteristic of the coincidence count going to 0. And both the photons going to one detector. It has got nothing to do with bunching at a beam splitter. Now the last part. Usually in a one photon interference experiment, there are more than one ports for the photons to go out. This means that whenever we are observing a minimum in the intensity at one port, the intensity at the other port is at its maximum, such that the total intensity is conserved. However, in the above experiment, the two photons don't have any ports other than ds and di. So how do you explain the photon number conservation when we are at a minimum? Where do the photons go? This is a descriptive type question. So when the coincidence count rate is at its minimum, it means that coincidence is not detected. So this does not rule out the possibility of both the photons going to one detector. The other way to think is that down conversion did not occur in the very first place. So either both the photons go into the same detector for coincidence not being observed, or the down conversion has not occurred. These are the two possibilities for us to not observe any coincidence. And for the double pass case, we have only this particular option, because in this case this is the situation for double pass that we discussed in this problem, and this is the case for Hongo-Mandel that we discussed in the previous problem today. So in Hongo-Mandel, there is possibility of both the photons to go into the same detector, but in double pass, as we saw from here, that the one photon count rate is same as two photon count rate. So in this case, the option is that the down conversion did not occur if we do not record any coincidence. Okay, so this brings us to the end of week 8 and today's lecture. If you have any doubts, please feel free to ask. Otherwise, the lecture is over from my end. You may now log out from the meeting. So if you do not have any question, please feel free to leave the Zoom meeting. See you next week, next Saturday at 3 p.m. for discussing week 9. We are now 2/3 into the course. 2/3 of the course is complete. Out of this 12-week course, we have completed 8 weeks, 2 months. Now only 4 more weeks, that is 1 month, is remaining. Hopefully you have learned many new concepts, and a few more concepts will be introduced in the upcoming weeks. Where we will look at spatial two-photon interference and also Bell inequality and orbital angular momentum of a photon. These topics will be introduced in the upcoming weeks.